coming to one of the other big CO2 producers in the world, that is cement industry. And I will share an experience about a decarbonization project in cement industry using Barracuda Virtual Reactor engineering. First, shortly about aixProCess. As Sunaj said, it was founded in 2001 by a colleague and me. We are located in the western part of Germany, in Aachen, right at the border to Netherlands and Belgium. 25 staff at all, and serving different industries, but major heavy industry, if you look around, with focus maybe on cement. Three pillars of our work. These are the engineering services with the CFD process simulation, some products. We are deep in cyclone technology, sometimes even selling cyclones. We are the German distributor of Barracuda Virtual Reactors, and we have some digital solutions which are not topic today. Well, having said that, coming to cement as one of the big CO2 producers, and what you see here is the Global Cement and Concrete Association's net zero pathway for cement industry. And as you can see, we are right here in the mid-20s, and what will be necessary to go down to really net zero in 2050 is a bunch of methods and activities. You see the big impact of carbon capture and utilization storage, and what I will be talking today is here the 11% of CO2 reduction coming from substitution of fossil fuels and optimization or enhancement of thermal efficiency. So that is what we are dealing about in a variety of projects. And just for those who are not familiar with the cement process in very short, it's a countercurrent process of the raw meal, calcium carbonate meal, and gas flow that's mainly coming from the cooler, going through a rotary kiln, and then entering the calciner section. And here this is a cascade of cyclones, of highly loaded cyclones, the preheater. And I will concentrate my speech today about the calciner. Rotary kilns with a very sophisticated burner. It was obviously not the main application for Barracuda, but the calciner, which is mainly an entrained flow reactor, certainly is. And what is taking place in the calcination reaction on the calciner is this split of CO2 from calcium carbonate, from lime. And so that is a main source of CO2 in the process. The other source comes from the fuels. Yeah? It's a highly endothermic process, and the fuels produce CO2, probably mainly to half, 50% of the overall CO2 coming from the process and 50% from the fuels. So there is potential to avoid this CO2, or at least shift it from fossil fuels to other fuels, which, well, may count as real CO2 reduction or not. That's, of course, discussable. What I present here is a use case of Ecocementos plant in Rio Claro in Colombia. That plant was commissioned in 2019 with a clinker production of 1 million tons per year. Estimated CO2 emissions 1.4 million tons per year. And what the operator aimed at is a reduction of carbon footprint, substitution of coal by solid recovered fuel. And to be honest, it's not only an environmental issue, it's a cost issue as well in the meantime. With that improvement of process performance, the introduction of any alternative fuels brings some challenges with it. and particularly keep the plant productivity and minimize the CO emissions, often a problem in cement producing. And particularly aiming at a cost-efficient solution, or you could say smart engineering, with not building a new calciner, which could be one solution, of course. But doing this in the annual turnover, so we have heard, of course, FCC have a turnover time of 5 to 6 years. In cement, it's very typical that they have one turnover each year. Maybe 4 weeks, something like that, and that is then they can do small modifications, and for a new calciner that would take them out for 3 or 4 months at least. So that is what they are looking for. What is solid recovered fuel? And if you look at it, it's very heterogeneous. It's a very broad particle size distribution. There is almost no particle of spherical shape. We have inhomogeneous shapes and varying particle density, and how to model that in industrial kiln. What we worked out, and that is published in the meantime and often applied, not categorizing the particle size distribution in the end, but the distribution in terminal velocity. And for that, with a partner, we are doing zigzag Zifter experiments, and then we are classifying certain classes of terminal velocity. And by identifying the model parameters of shape, size, and density, we then come up with one-to-one modeling the zigzag Zifter experiments with different classes of terminal velocities for different fuels. From that we have a kind of a library, so we can easily put in those representative fuels or representative terminal velocities into our model. And there is a fourth parameter that is the material, because we always have different alternative fuels categories, as I will show in a minute. So the kinematics of or terminal velocity is the one thing. The other is the, here should be an animation. No, obviously that doesn't work. But what I wanted to show here is that we're doing combustion experiments here, where we can identify the intense flames and if you and the weak flames and the char oxidation. And here we go. Yeah, thank you for that. Yeah, and the other one in comparison maybe. All right. So anyway, from the experiments on combustion, we can deduct the different evaporation or devolatilization kinetics. So it's a gross kinetic, of course, but it serves the purpose very well. And you see there are high differences in for such foil material. We are talking about 5 seconds until complete burnout, and others, more lumpy fuel, we are talking about a duration of 35-40 seconds. So again, another heterogeneity here. This is the domain we are looking at. In Barracuda, you see here the end of the rotary kiln section. This is the so-called calciner, pot calciner, with the upper pot and the lower pot. Here is a section to the bypass where chlorine is separated. There are still 2 coal burners. There is a bottom and upper meal box, and we are looking not only at the calciner but at the bottom stage cyclone as well. The Barracuda model is not too big. We are talking about 500,000 numerical cells, roughly 1 million, 1.5 million parcels. And we have a series of embedded Barracuda models we are using, and then some in-house models for the meal calcination, for core and shell alternative fuel combustion. So we are not looking at the particle at one entity because the thermal diffusivity is very low for some of them. And well, I won't go into detail of any of these models now. The process of what we call CFD engineering or computational engineering, this is what the baseline scenario, and as we heard yesterday, it's always good to come from a baseline scenario to test the model and see if it does what it should. And here is the future fuel scenario as stated by the client. Going down from 13 tons per hour to 5.8 tons per hour for hard coal and substituting with solid residue fuel and tire chips, almost to the same amount. You see that the overall calorific value remains more or less the same of this fuel mixture, and this ends up in the thermal substitution rate of 55%. Starting with the as-is fuel scenario reference, and then, let's say, trying what the plant does with a base future scenario, we then enter an iterative process of modifying the geometry to some extent, improve process conditions, and ramp up the amount of alternative fuels, and then finally come up with the final future fuel scenario. And typically, this takes 3 to 10 iterations, well, depending, of course, on process experience with it. To quantify this, we have different criteria. We have the KPI of degree of calcination, DOC. We have to reduce meal and fuel spillage into kiln inlet. You'll see that in a minute. Increase or at least maintain the degree of burnout and minimize CO emission. And a bit as a sidetrack, if you have to evaluate all these parameters and for different fuel types, so there's a matrix of parameters you have to look at for each of these variates. We found it very useful to use TechPlot and automate TechPlot to do the evaluation for us. Because typically when we are creating these post-processing templates for the meal calcination and fuel burnout, that is a very tedious process, and if you are in lean management, then it's clearly a muda, very annoying to do all these things. And with now completely automated post-processing with Python scripting of TechPlot and making use of the various libraries inside TechPlot Python, we were able to go down to 20% of the man-hours saved for the entire projects. And you see that is mainly to the reduction in post-processing here, and in the end really giving us more time for doing the value-adding features like the engineering itself. So that has accomplished, is now embedded in each and every of our calciner projects, and of course we apply it for other projects as well. Well, just some of the optimization deliverables. I won't go too deep into each of those variations that should not be of interest here. But what is the result of what we call computational engineering is the selection of the right feeding points of the alternative fuel material. It's the feeding concept, pneumatic or gravity. And of course, that has an impact on mixing of these fuels into the entrained flow in this reactor. We give clear advice on the fuel engineering. That means size and moisture of the incoming material. What is the calciner capable of without major modification. And it's more economic to put a pre-processing step for the alternatives up front. That can be a dryer, that can be an additional crusher or a mill, instead of changing the 50, 60 meter height calciner. And then we, in the second step, we concentrate on thermal efficiency enhancement, eliminating some process deficiencies and enhancing the process stability. And yeah, now it works. Here are some comparisons just to give you a feeling of how that looks like. Here is the comparison from the as-is fuel scenario and the final fuel scenario regarding the degree of calcination. And of course, we are mostly interested in the degree of calcination at the end of the calciner, before the material is separated in the cyclone and then goes into the kiln. You see that here we clearly reached the target of maintaining the degree of calcination from the as-is scenario to the new scenario with 55% alternative fuel. From the automated analysis, of course, we can look in between where is room for further improvement, how is the process of calcination along the reactor. Then looking at CO, and here we are again comparing the as-is scenario with the final fuel scenario. We see that we are able to eliminate 40% of the baseline of CO, although the new fuels are more difficult to burn. And you can see it here in the cyclone. We still have a streak of CO here in the cyclone in the base case. Then temperatures are below 800 degrees and no more CO oxidation is taking place. So we have to complete the CO oxidation mostly in the calciner. Well, then looking at the next KPI, the meal and fuel spillage, and by that I mean we have here the fuel inlet, and here is typically in cement they call it the orifice with velocities of 40 meters per second, and still there is some meal and often the more lumpy fuel is raining down through this orifice and directly getting onto the bed and leading to some local reduction and lack in fuel in product quality. So for the SRF, we achieved from the base future scenario already rather low rain out, lower than 50 kilograms per hour. Looking at the burnout, we were able to further optimize this from 3% to 1%, which is actually good. Yeah? Then further on to here you see the motion of the particles. Of course, very useful to identify in this iterative process where to look at, where do we have to have more mixing and retention time for the, because you see, we have a gas retention time of, let's say, something about 4 to 5 seconds here, but we have to burn a fuel that needs maybe 40 seconds to burn out. Yeah? So that is a bit the art in designing here. Well, then the TDF, and here with the base future scenario, we have a quite significant rain out of 300 kilograms per hour. You see we are guiding some of the material here in the cyclone in the base future scenario, and with the further engineering we keep it here in the calciner section, mostly in the lower calciner section, and get the rain out down below 50 kilograms per hour, which is typically a good value. can further reduce the burnout, although there is obviously some room for further optimization still. Yeah, and with that, I'm at the final results or the takeaways of how Barracuda Virtual Reactor can serve for cement industry and particularly for the calciner optimization. And we clearly see that it contributes to decarbonization, and this alternative fuel ramp up is one of the hot topics in cement industry all over the world right now. The other one is now coming up as a preparation to carbon capture, running the process under oxy-combustion conditions. And again, we need for those projects Barracuda because very similar to what we heard in the closing session yesterday of the PSRI conference for decarbonization of FCC. With the recycling of CO2, we changed the transport conditions in a fluidized bed or here in the untrained flow reactors, and that is what we have to take care of, and that is the transport conditions. It's heat transfer and mass transfer, and here in the calciner with an increased CO2 partial pressure, it's then the reaction kinetics of the decarbonization of the calcination reaction, sorry. Well, as a result, now we did this study last year, which is very typical. 1 year before the modification, we do those studies. And then the use plant was successfully commissioned in Q1 2024. And right now, we have the feedback from the customer that they are able to, in a stable process, to substitute 55,000 tons per coal. That corresponds to 51,000 tons per year in CO2 emissions, so that is reached the target. Yeah, well, it's easy to say that no other software can provide us, and we are using other softwares, by the way, but for those applications, no other software can give us the same stability, speed in executing those projects. And particularly the automation of the evaluation with TechPlot, that is not saving us time only, but I can clearly say it brings more satisfaction to the staff executing it. Yeah, really, we were suffering from these hour-long annoying things like, and it's very error-prone, yeah, and now we hit a button and let it run for a night, and then we have the full automated analysis with really nice pictures. Yeah, and well, of course, as I said, we're not only using Barracuda for cement, for other things as well, but probably what is the best feedback that is here by Carlos. He's the person in charge for sustainability projects at Ecocementos, and we did a LinkedIn post about that project, and he commented to that post. I'm not sure if you can read it. It's so important to do the CFD to increase the TSR with alternative fuels. And well, he did not thank Barracuda because that wasn't background for him. He thanked us, but that wouldn't be possible without the application of Barracuda. Yeah, thank you for that, and open for questions.